My name is Andrea. I work for GeoSolutions. We are an international company with offices based in Italy and the United States. Engineering having company with support of several open source projects in which we participate as core developers, and we provide a number of services around them. We believe in open source, in open standards, and well, that's why we are here. So let's talk about big data first, since this presentation is about one particular case of big data. What's big data? Big data can be defined by the three V's: velocity, volume, and variety. You have a big data problem when you typically have all three. So a practical definition from Wikipedia: big data refers to data sets that are too large or complex to be dealt with by traditional data processing application software, and so you need to resort to something else. Now, in this case, we are talking about maritime applications. So let's have a look at the functional needs. Maritime data is produced by a large variety of sources. All the ships above a certain size have sensors that, well, communicate the position of the ship with a variety of messages that are sent through either satellite or terrestrial networks to the authorities. And there is also not just the ships, but also the ports, the navigational aid systems, and so on. So we have a very large system of moving points, but also a significant amount of static or semi-static data, which is all the infrastructure. The use case in number, we receive 50 million positions reports in 24 hours, and we have to handle 500,000 different ships, which is interesting. During the peaks of activity during daylight, it's 2,500 messages per second. The Azure data lake that contains all the data contains 7 years of data with 125 billion positions inside. So not something that you would store on your laptop, let's say. So all this data is used to provide and to support informed decision-making for maritime traffic monitoring, search and rescue operation, environmental marine disasters monitoring. And to do that, we need to combine a variety of different data sources. Yes, we got the positions from the ships, but also we got fisheries data, we got ship registries. So as the data comes in, it needs to be enriched by crossing it with all the other data. Interoperability at this point is important. It's important on the input side, it's important on the output side. On the input side, it's important because not all the data is managed by this organization. It's fetching data from outside, so it needs interoperable means of getting the data, but also the data produced by this organization needs to be used by a variety of others. So again, on the distribution, we need interoperability. And so that's why OGC services are so important. We have implemented a number of scenarios with the WMS, WFS, and WPS. We are going to talk about 2 specific ones, but there are more. So visualize in real time all the ship positions, which are changing all the time, and there is this very large flow of positions and updates coming in. Density maps of the ship tracks, competition and visualization. Visualization of real time of navigation to aid systems. Detect the ship positions and correlate them, because sometimes ships meet in the middle of the sea to do some unsavory business that they shouldn't be doing. Yeah, that's a use case. Electronic navigation charts for the navigation, and historical ship positions and visualization. So we got this large data lake of all the positions for the last 7 years, and you can query it interactively. So another thing is that all this data is sensitive, and different stakeholders need to see a different subset of it. Some are limited by time, some are limited by topic, by nationality, and so on and so on. So there is a very sophisticated authorization system that ensures that everyone can see only what they are supposed to be seeing. This also means that it's very difficult to cache anything, because every user gets a slightly different picture of the available data. So let's have a look at some use cases. Visualization of real-time ships positions. So we constantly have to display the latest position of each known vessel for the last 24 hours. The system is designed to handle 5,000 positions per second, and that's a lot of positions per day. Positions come in through the various means of various messaging, and they are enriched, actually validated, enriched, and processed before GeoServer can display them. So imagine this, this constant flow of messages that are thrown at you, and you cannot just have GeoServer handle them directly. You have to ingest them, enrich them, validate them. So there is this large flow of messages that should be handled in an asynchronous way until we are good and ready to put it in a database where GeoServer can do something sensible with it. To do this, we have developed a Kafka cluster that can do all this async processing from the messages down to the database. And then eventually this goes to PostgreSQL and or also Oracle. It used to be Oracle up until some time ago. And then the GeoServer cluster can do mapping and searches and so on top of it. So having a write-intensive environment is another challenge which makes things interesting. Most of the use cases that I know personally out of GeoServer, they are read-intensive. I have my data, I serve maps like there's no tomorrow, but the data is not updated all that often. It is updated maybe daily, maybe on an hourly basis, but here we are talking about thousands of messages per second. It's write-intensive. And this changes the balance of how you design the solution, because you have to be able to write fast enough, not just to read fast enough. So you have to, change your data structures so that it's going to write fast enough. So to do that, we have Kafka screens, but another thing which might sound very strange is that we don't store positions in points in PostGIS using spatial indexes because they cannot sustain the write rate that we need. Right? We do X and Y columns with B-trees instead because they can. So this is one, strange outcome of having an environment that is write intensive, and you need to have the right data structure on the back, and apparently the old way is actually fast enough. As I said, advanced authorization. Everyone needs to see exactly what they are supposed to see. We use a variety of things like a custom authorization subsystem. GeoServer allows you to write with a little Java class your own specific authorization subsystem. We have a built-in one that authorizes just layers. We have geofence that allows to mix and match, the current user, the current service, and decide to filter the content of the data based on attributes and so on. But for use cases like this, we typically go custom and write something that is driven directly from the customer database. We use GeoServer SQL views to control better the final query, typically because we have to join several tables to get to the right authorization and so on. And as I said before, it's difficult to do any caching, but we still do some opportunistic caching for a subset of the users that are having the most stringent needs and that are representing the highest amount of traffic. So this is a map of all the ships in the European seas, where each vessel is colored according to its type. We have a position, we have a direction. Coloring can change based on what I want to see. The vessel type, the vessel age, in this case, we are focusing on fishing vessels, and we color them based on the fishing gear that they carry, and so on and so on. And all of this is continuously updated on the screen of the maritime controllers. We map on the fly also any navigation to aid system. In this case, we have a search and rescue operation ongoing with an aircraft, which is here, and the path that it has followed. So apparently something was going on in this area. We have the position of all 8 navigation system positions. Think buoys, but it could be much more. And we're a project on the fly depending on the use cases. So in this case, we are seeing a polar projection of all the ship positions. And the system allows the maritime controllers to do some highlighting. So let me see all the ships that have this kind of fishing gear. Let me see all the ships that are carrying, I don't know, containers, stuff like that. And you can have multiple highlights deciding different colors. And all the highlights are going on dynamically as the ships move. To do this fast enough, we actually had to make some improvements to GeoServer. So this is a map showing all the cargo vessels with all the other vessels going around. So this is an example of highlight with probably 100,000 vessels in the view here. Okay, another use case is historical vessel tracks visualization. Now, what I've shown you right now is focusing on the last 24 hours. We keep the data in PostgreSQL. It's small enough that we can keep it in a traditional database. Here we are switching to historical vessel tracks. So, the 7 years of all the positions of all the 500,000 ships. Too much to store in a classic database. So for this, we switched to Azure Data Lake, which can contain very large datasets. In this case, the 125 billion positions. And we made it available through GeoServer, OGC, WFS, WMS, and WPS. Now, the thing is, Data Lake is very capable. It can contain a lot of data, and you can run processing on top of it. But if you are focusing on a particular area, it's not like you can pretend to have WMS quick response times fast enough, you have to go into the data lake, extract the data that you want for one particular ship, for one particular area, and that might take a little while. So the idea here is that it's not fast enough for WMS, so what we are going to do, what we are doing, in fact, is that we have the Azure Data Lake, we have an Apache Spark endpoint that fetches the data for me, that takes a little while, then caches the result in a PostgreSQL database for quick usage for every subsequent WMS and WFS request. So we have this Databricks data store, but the data store per se wouldn't be fast enough for interactive display, and so we have the local PostgreSQL cache. So yeah, we do these queries. We do them in SQL. It's kind of nice. Databricks allows you to stick in data which is alphanumeric and then treat it as if it was tables in a database. So you have this SQL interface to the Databricks content. We use it to do the queries and to do the extraction. When you are dealing with this kind of data volume, how you represent the data in the storage makes all the difference. You lump up the data in blocks, and the way you structure it favors one use case, time series extraction, and totally destroys other use cases like space query. So you need to know which direction you are going to take when accessing the data in advance and optimize for it. And that's exactly what we did in this use case. So we allocated the data into Databricks so that it would favor the two kinds of extractions that we need at the expense of other possible use cases. As I said, it's too slow to do it on the fly, so we are caching and we are also downsampling and pre-processing the data so that we don't get too much data out of Databricks. In the particular case, we popped up a new vendor parameter that we stick into the get maps, which is the Databricks query. And the first request is slow. It's going to take some time to do the fetching from Databricks and so on. And any subsequent query with the same data, with the same vendor parameter, it's going to be fast because it's going to be running from the PostgreSQL cache instead. So we got this Databricks data store with extra configurations on how to, store the cache and how to connect to Databricks and so on. You have, there's a geometry generator thing, because in Databricks we cannot store points, we store attributes, alphanumeric attributes. So we have to go back from, points to, to XY to points. So we have a custom configuration that we plugged into GeoServer. I think this is a nice use case of how GeoServer is extensible without having to change the core. So this is the user interface. We plugged in a new panel without having to do any change in GeoServer core to build the position out of alphanumeric attributes. This demo that, screenshots that I'm about to show is going to show 2 vessels for 6 months in year 2021, their movements. And we will find out in a moment why we are interested in those 2. So 2 vessels, one red, one yellow, they go around a while. You can see that they overlap in space, at the very least, somewhere near Singapore. And if we look more in detail, we can find that actually the sharing is suspiciously close, the sharing of positions. So this kind of use case is really trying to find vessels that met at sea to exchange goods or whatever, where they weren't supposed to be doing that. Another thing that we can do is an area-focused search. So we say, okay, let's focus on this area. Let's get everything that we can out of that area. And so again, another selector for a particular bounding box and a particular timestamp. And what we get out of it is lots and lots of positions for that time range, all the ships that were involved in that day, in that area. And again, we can then explore the dataset and find commonalities. Not very visible in here because there are too many. Then we can maybe drill down by vessel type, or since it's in PostgreSQL, we can select the data as much as we like to extract subsets of it quickly. And as I said, this is used by maritime authorities to find whatever might be going on at sea that wasn't supposed to be happening. And that's it.